a number of things that sort of preliminary things I just want to touch on. So this is a book that was with John Conway that, even though the senior author is no longer around, we're going to have a new edition of this coming out. But I kind of want to sell this. The whole idea here is that this is a modern, powerful approach to two-dimensional symmetry of a plane, a hyperbolic plane of a sphere.
Is it possible to click the OK, or clicking OK is too hard?
Oh,
That's a little weird that we can't get the cursor.
that's so weird.
Maybe not.
It's another one of these things.
Maybe
Sorry about
that's
that.
the recording happens.
Peter, can you hear?
I don't know why it's been so weird with the cursor. Yeah, maybe it's
Because
because
it's play mode or something.
it's something to do with. I'm sorry about that.
Yeah.
Yeah, I'm sorry.
Okay.
So anyway, the thing is that really the idea is to really get rid of. Yeah, I see the problem. It's awful. It's terrible. You can't see the slides. Okay, maybe we need to rethink something here. Yeah.
Oh, now you have to click the OK.
What's that?
Do the OK now.
Okay.
Oh, now.
Okay. And
There we go.
Drag this
Drag
off
it
of
down.
the.
Drag it down.
Sorry, this feels like took a lot of time just to get started.
It's our fault.
It's always our fault.
So let's try this again. And I don't know. Okay, so the idea here is that with every symmetry, you just take this person had this idea of taking the quotient of whatever space the group is acting upon and then analyzing those. And that turns out to be very powerful. In 3 dimensions, it's too hard. It doesn't really get you anything. But in 2 dimensions, you have the power of the classification of surfaces and then this very powerful and sort of unexpected geometrization of them as well. So that goes beyond. Anyway, so that's great. And then another thing I'd like to sort of ask you all, to tell you all about is this thing, which is, would you like $25,000? So MoMath has an annual teaching prize, and the idea here, and it's really for the K through risk 4 through 8. But I think I actually have won this, and I really think it's important for math faculty, for research math faculty, actually thinking in these terms. And I really think it's very important. Is there something that is in your world, your mathematical world, that you can pluck it out and get rid of all the extraneous stuff that you can tell graduate students about? Literally, take something from that level, and then what's the one thing you tell an 8-year-old get? I mean, seriously, that's what this is about. So anyway, that's really great. There's and then the motivating question for today, which is sort of, and I think it's really fascinating in a lot of ways. And as combinatorialists, I mean, I'm sure you're sympathetic to this. So the basic point is when shapes fit together, how complicated can that be? And of course, we might mean this very broadly. So, for example, in the natural world, this is like everywhere. All over the place, we see complex systems arising from the interaction and assembly of simple gadgets. I mean, just sort of a little bit of a grandiose version of this, but absolutely true. Is, of course, the very nature of proteins themselves and the way that proteins are basically the geometric, electrical, mechanical gadgets that do all kinds of amazing stuff. And then for that matter, I mean, mathematical logic itself. I mean, when we get down to mathematical formalisms, they're basically logical fragments behave in sort of similar ways. And this is sort of, went to a conference last summer, which was on the state of the art for soft matter physicists. So this is actually contemporary, basically, of what's the optimal packing of spheres inside of a cylinder. And I think some of you, if any of you are geometrically minded as combinatorialists, you would realize that these problems are really intractable. They really are very difficult, and that this is 2024 state of the art isn't really too crazy in some sense. And that this was down at the deli on, this is beyond the state of the art. But it's kind of an interesting question too. What's the loosest packing you could have with something? And then one of the things that I do, and I would like to just sort of advertise this for your math clubs and so on, is I do a lot of participation art where people come together and make things. And so of course, self-assembly is a big part of that. So here's some negatively curved surface, and New York Math Fest is coming up, and you're downtown. And so if you're in town on the 13th of July, and then this was just made last month. So this is another thing at CERN. CERN, if you go to CERN, you might know outside of Marseille, then just in the last couple of years, I don't know when, but just the last very small amount of time, there's suddenly a lot more mathematical art. So that's good. And then another one of these. By the way, this is the Klein quartic. This is a new rendition of the Klein quartic, so that's kind of fun. But of course, you have to complete the model by attaching opposite rings, which is but with a quarter twist. And so again, these are, I'm interested in assembly for as a practical thing as well, even to the point of this thing. And I guess I would like to say again that if you would like something for your public facing event or something with your band club or something, I'm available and in town. So this was something that we did quite a lot of this year for whatever reason. This is last summer, and then this is just last 2 weeks ago. And so I think you know what this is about. And so actually the self-assembly of these guys is a whole topic unto itself. The local assembly. So here we are sort of at the beginning of the talk in a sense. I think, is there any chance that nobody heard about this? I don't know, it's sort of media saturation for a while. So of course I will introduce it properly, but it's not like the punchline is a secret here. So this was the first so-called aperiodic monotile, and just a year ago, just 50 weeks ago. And in fact, even and then we have what we about the other schemes and reflected or not. And I guess again, I really should emphasize that Dave Smith is the discoverer of this, that I'm sort of the reporter in some sense. So, and I have more to say about the roles that we played. But this is really, I think if you were around 50 weeks ago, you probably might have seen this incredible. I think as mathematicians, it was absolutely unexpected and overwhelming to see a result play like this. And of course, immediately it was pointed out that it wasn't a hat at all. Sure, and it was right. And one of the things that I learned about fairly recently was kind of amazing, which is that Dave and Craig, before I was involved, they were, Dave invited Craig in, and that they actually knew. They said it looks like a shirt, but we'll call it a hat. Amazing. And then there was this thing which was really amazing, which was sponsored by these wealthy people at the bottom, and we had a couple hundred of really incredible entries. So this is a kite made out of a hat shape, made out of kites, made out of hats, made out of so that's very clever. And then this was one of the winners, which just delighted us because it's so ridiculous. So of course, when it's served, it's a lot messier. And then so I actually have scores of photos. I'm just going to show you like 5 or 6 or 10 or something. So this is we had a lot of food entries. We had a lot of fabric entries. This was one of the nicer quilts, but lots and lots of quilts, lots and lots of jackets and clothing and prints. I really like this purse because this is a child entry. So the adult and children categories. And she actually, I don't know if she did this on purpose or not, but the color arrangement actually plays an important role in it, which is cool. So I don't know if, it has a moment. And then this is hand painted, which is amazing. And then this one I really like because, so this was on the internet for a while. This kind of bounced. Sorry. This was on the internet, and this kind of plays very nicely into the symmetries of things. So I contacted the author, and sure enough, he knew. There's a way to tile periodically with the hat if you allow hexagonal holes. And so he realized that, and this is exactly on theme, that you can change the idea of the symmetries of things is that you can just sort of tweak the numbers, and you would sort of move fluidly from, say, planar to spherical to hyperbolic geometry. And so that's exactly the idea that this guy, John Paul Wheatley, had. But I think this is really amazing, is that he had imitators. That John Paul Wheatley's idea was so good that he actually had imitators enter the contest, which I think is really lovely. And then we had this entry, which is so ridiculous. I love it. But this kind of violates the spirit because it's a single tile. And this one is just, it's incredible in its own right. And some of you got that. I didn't get that until I was explaining to it. So maybe there's an H thing there. I'm not sure. Does somebody need to know what that means? There's like rickrolling. Rickrolling. See, I didn't know that.
I'm still missing it. That's okay.
I'll explain. And then this one's great. This is a hat bubble wand, but it's very disappointing because they still come out spherical. So anyway, that's where we're, and then of course, just to sort of put a few other things into play, there were some really nice mathematical reactions. There's been a lot of written about it, but just sort of some key things is that in this literature, there were all these tools that were developed to analyze the spaces of these. Like once you have an example to sort of analyze it, but there weren't any examples. So within like, it was kind of funny, really. It's like once within like 3 weeks of the publication of the hat, all these tools people were just so excited to get to apply them basically. And so this is an absolutely wonderful paper with a lot in it, a lot of important things. And then similarly this one, which I guess is blocked there, but this is by Josh Sokolar. So this is like a diffraction pattern, which is important for in a certain direction. And then, okay. So all of this is so what I really want to talk about today with you all is to put this in some sort of context that I think makes some sense to combinatorial people. And for me as well, I mean, this is sort of the direction that I come at it. And so, and then I'll also, so I'll talk about this for a while, and then I'll be able to touch on some details of the proof as well. So, so what is an aperiodic monotile? Well, to get there, we can just ask this sort of really almost insultingly easy question, which is, can copies of this tile, of this shape, form a completed tiling of the plane? And I think you got that. So even math PhDs can come up with a reason why that's true. Like we would have to have some sort of abstract understanding. But in any case, it's obvious. And then for other examples, okay, you can understand why that. Like an obvious proof would be to try to stick it, to actually do it, and you have to put a point there, and then you don't have any further room. So that's obvious. But in general, and then the word monotile just refers to if a shape does admit a tiling, then we call it a monotile. And that seems to be a fairly new coinage, in fact. So, but the real question is, how can we tell? What would be a process in general by which we might be able to answer this and understand this question? And so here's another example, which may not be obvious, but in a moment it will be. This one can tile, and it can form exactly 3 concentric rings, but the fourth ring would not be able to be completable. And why is that? Well, this one has a proof, a fairly straightforward proof. The proof is that if you look at the tile a little more closely, it has it's made of hexagons. And some of them have indentions, some of them. And then in any actual tiling, these the innies will have to match the outies, except on the boundary. Any mismatches will be on the boundary. And so, but of course, there's an imbalance of 3 per tile. So every tile introduces an imbalance of 3 indentations. And so what that means is that those have to lie on the boundary. But then approximately, at least to some order, that as you increase the combinatorial radius, so as to say the number of rings out, the number of tiles will grow roughly quadratically. Will go quadratically up to some fudge. And then the boundary, of course, will grow roughly linearly with some fudge, but of course, the fudge will not matter. Eventually, the quadratic will outstrip the linear. And so it just happens that it's 3. So why is it 3? The question of why really comes up a lot, because when you have these things, there may not be a why. There's a mathematical formal why, which is in the form of a proof, but the proof is so tedious that it's not really accessible to a human. And moreover, one would want some sort of design principles. When we say why, we don't mean like, give me a telephone size book. proof, we mean something like, give me some principles that I can actually use. And in some really fundamental sense, I believe there is no lie about these, just as there would be, as I'll get to, in any situation where we have some fundamental undecidability stuff like around. So here we have this question, which is our Heesch numbers unbounded. So you can't see it, it's covered up, but this is Heesch number 6, meaning that it has 6 concentric rings around. And this is the world record as of 2021. And so we might ask, are they unbounded? For any n, is there a tile that you can tile at least n rings, but you cannot complete to a tile? And that's an open question. And then here's another example, which just to kind of distract you and have some of that. And I would like to have left, unfortunately, the Monas laser printer is out of commission because of the move. Otherwise, I would just be giving heaps of these to take with me, but I've asked for them back. But you might just sort of play with these a little bit. I'll just sort of set them going down the table. And these, you might ask, okay, do they tile the plane? That's the question. And I think if you play with these for a few minutes, you will immediately see that you have no idea. And that's important. Because so this is to sort of spoil it, this is they do tile. This is the simplest possible tiling that they can choose. So that is to say that they can form periodic tilings, but the smallest fundamental domain has 10 different tiles. So another way to put it is they form, there's a symmetry group that X here, but the tiles are intended to be, or there's lots of ways to say it. But we call this isohedral number. That's to say, that's the size of the smallest. So isohedral number 10. And this is also a world record from 2003 by Joseph Myers, who was one of the co-authors of the paper. And so we again ask these isohedral numbers. Yeah, this is also another question. These are stand-ins for like basically how complex can a shape be, basically. Here's another example from the same search, the same era. This is the second best example of isohedral number 9. It bears noting that this is from a search of over 1 trillion different tiles. And that these two examples I just showed you are the only interesting examples that came up of over 1 trillion tiles. So it's really raises some questions about what asymptotic complexity even up with. I mean, is this it? Or the end line, or is there? Okay, so we still have that. So now I think some of these kinds of ideas will be familiar to you, I think, to many of you from other perspectives. I mean, basically, we have the situation of asking, is there an algorithm? Is this such and such decidable? And we have in some sort of combinatorial setting, which is kind of a fairly common situation. And the way it played out here was that in 1960, this emerged in the context of some, we're actually still wrapping up some part of Hilbert's program from 60 years before that. And so in the context of whatever it was, Wang pointed out that if you, that the so-called completion problem, at least, is undecidable. So if you have a set of tiles in the Euclidean plane in the starting configuration, it's actually pretty easy to see that you can't complete that to a tiling of the whole plane. So here's a typical little Turing machine run, and I'm not going to explain it, except there's the transition table. But on the right, we have, a little image of the Turing machine tracking through time. And the point is that you can tell if this picture is right just by local information. I can look at this region and I can tell you, did it violate the rules or not? I can look at this region where O just becomes O, and that read write head is nowhere in sight. And I can tell you, does that make sense? There's a match between local configurations here and what the Turing machine is supposed to be doing. And so, in particular, that's very easy to convert to tiles. These tiles are just local configurations. And so here's a collection of tiles that would exactly encode the run of that machine. So starting from here, but it has to have the seed tile to get the head read write head going. Then everything else is more or less just mechanistically determined from trying to emulate this machine. It sort of sends a string of tiles out that way, and then the O's have to follow the O's, and so on. And so, in particular, this configuration can be completed if and only if the machine doesn't fall. And that's undecidable, so therefore the completion problem is too. Okay, so But that doesn't actually answer the question of how can I tell if a given set of tiles admits a tiling, period? Because in this set of tiles, I could just do the dumbest. I mean, this set of tiles, no matter what, definitely admits a tiling, namely that one, where I just do that. And so the question is, how can we force this undecidability in some sense? And so that was, so in general, the question might be, how can we decide if we can take shapes, one shape or many shapes, and ask if we can form a tiling? And so this is what Wang basically pointed out, is that if you enumerate larger and larger patches, you can discover if the tile, if it doesn't emit a tile. It's decidable if it's what we might call semi-decidable. I just get enumerable backwards forward. So I just semi-decidable if we it will halt if it does not emit a tile, but it may run forever if it does. So because if you don't emit a tiling, then there has to be some size disk that you cannot cover, because the contrapositive of that is that if you can cover arbitrarily large size disks, then you can cover the whole plane. Now that sounds obvious, but there's actually kind of a little compactness. There's a little bit of a trickery to make sure of that, but it's in the end it's as true as it sounds. Just kidding. And so that means that and there's a flip side of this too, which is that if we I shouldn't really say consequently, but in addition, if there's a bound on Heesch number, then we can also decide the monotile. We can decide the problem, monotiling problem. Give me a tile, and if I know what the maximum Heesch number is, then I just enumerate out to that size. And if I make it that far, then I'm home free. So that's a connection between hang on. So a monotile is aperiodic if it cannot form periodic tiles. And so in particular, then we would have a decision process also if there were no such thing as an aperiodic monotile, because we could then sorry, this seems to be a bit out of sync. So also more generally, not just for a single tile, but we can ask for a set of tiles being aperiodic if they emit a tilings of the plane but don't emit periodic. And so, sorry, this just seems a little, sorry, I'm not sure, the slides just seem a little funky. I'm not what I expected. So I guess, so in particular, how Wang conjectured that there were no such thing as aperiodic sets of tiles. Remember, he had proven that the completion problem was undecidable, but he conjectured that we would always sort of, in a sense, need that blank tile, that you wouldn't be able to actually control the computation enough. And so I'm not going to translate this. This is for people that really love, in the field, love to see this slide, because then you can see how the language has changed and everything. But basically, we would say that Wang showed, and I'll explain the proof in a second, since that if the domino problem is undecidable, then there would have to be an aperiodic set of tiles. And what he meant by this, and then he conjectured furthermore that the domino problem was decidable and that there would not be an aperiodic set of tiles. And it turned out that that was not right, that it turned out that there was a method it was undecidable for multiple tiles, and that roughly equivalently, the finite version of this is that there are NP complete problems. So, okay, so this is what was, I'm sorry about that. This slide should have been a little while ago. So in particular, if there is no such thing as an aperiodic monotile, we would have a method to decide the monotiling problem. And this is more general too. So if there were no such thing as an aperiodic set of tiles, then we have a method of deciding the tiling problem, whether or not a given set of tiles is tiling. And the connection is this. So if this is undecidable, then the Heesch number has to be unbounded, and there has to exist an aperiodic monotile. And basically, the algorithm would be, if there's no aperiodic monotile, then the algorithm would be enumerate larger and larger patches. And if it doesn't tile, then you would run out of patches to enumerate. And if it does tile, if there's no aperiodic, so there's no aperiodic tiles, if they do tile, then you would eventually have to find some fundamental domain. That's the part. Seems to be the slide that's missing. So you enumerate larger and larger patches, and you either run out of patches that you can tile, you know it doesn't tile, or you would find some fundamental domain and you would know that it tiles periodically. And there'd be no third possibility if there was no such thing as an aperiodic set of tiles. But that's not the case. We don't know that. We don't know that. We do know that. Similarly, we have for isohedral number, I won't go into this, but there's sort of a related problem, which is whether or not a given set of tiles admits a periodic tiling, and it has the same sort of implications. And this generalizes quite a lot. So this has been a pretty productive framework for about 25 years, I think. So we have this generalized set of questions, which more or less, this is taking the place of the monotiling problem. Does a given set of tiles include tiling? And this is the completion problem that we have discussed. And there's a few other things. We start to distinguish between strong and weak aperiodicity and so on. But there's this little network of logically related questions. And it's been, I think, pretty productive. So we might ask, in a given setting, which of these hold? And now for the plane, for the Euclidean plane, this is well known now for 50 years that all of these all get checkmarks. But for, wow, it's weird. This is just somehow, for a single polygon where we have translations only, we have absolutely non-trivially, these are all decidable. And by super non-trivial, because to show that with polygons by translations of, that there's no such thing as an aperiodic set of tiles is so to the point where recently we have this result by Grenfell and Tao, where if we allow ourselves a finite group extension, which is a huge finite group, but still finite, then we have all of a sudden these things become, there's enough room to suddenly get this undecidability stuff going on. So this is just by translations, but where you have an extra group's worth of information to look at. And then in the hyperbolic plane with multiple kinds of tiles, we have this kind of literature. It turns out, I want to explain what weakly is right now, but we'll come back to this example in a minute. But it's this is an old example. This is exactly the same thing that I showed with made out of foam before, this beautiful curvy foam businesses. This is the same tiling in like the map data. And so, and similarly, the completion problem is pretty simply undecidable. We know this, that we know that. We still don't. And then more, this is I guess this slide has not been edited properly, but in the context of geometric group theory, which is, I don't know how closely any of you might know that, but geometric group theory is just group theory, but where you really pay attention to the Cayley graphs underneath it. And then most importantly, look for invariants that don't depend on the graphs, but on the groups themselves. And so in particular, tiling by tiles, wag tiles are just square tiles with shifting around. And so this gets translated into subshifts of finite type on Z plus C. And then we can ask whether or not these so-called subshifts, which have played the role of tiles, in effect, are empty, which is, can you actually form a pattern of a particular nature with these locally defined rules. And so we have these kinds of the same implications again. So the sort of non-emptiness, we have the exact same kinds of phenomena. The non-emptiness problem is undecidable, would be implied. No, this is backwards, sorry. These arrows are in reverse, but other than that, it's right. So, and then just as a, one thing that's really kind of a foundational result there, which really puts it in solid ground, is that, so in geometric group theory, you really aren't interested in necessarily in individual groups, but in sort of their global nature, their global structure. And so that is to say, invariants that are preserved under what's called quasi-isometry, where you can distort things locally to some bounded amount. And so the existence of so non-emptiness being undecidable, or the existence of these aperiodic subshifts also turns out to be a QI invariant, which is pretty cool. And I guess this is a little far afield for this group perhaps, but I think these are some cool results. So on one-ended hyperbolic groups, we can do this. And on the lamplighter groups, it's now done just as you can't see down there, but this is 2024 by Bertoldi and Salas. So, okay, so back to the, what's happening now?
12:35.
Great, so we're doing great. So let me just describe, that's sort of the general context of how complexity, these kinds of complexity questions play out in sort of tiling as very broadly defined. And that's sort of been that little outline has more or less been my guiding light for a long time. I think many of us. But within the question of actually how aperiodic sets are made, so that Berger was one of Wang's students and famously constructed the set of 20,000 tiles, as well as proved that the domino problem was undecidable. And the way he did this became the basis of basically lots and lots of stuff for the next 60 years. And I should add, though, that this is just one, like 0% of the possible methods, because we have this undecidability result, right? Which means that we'll never, this is actually something we can check for, therefore it's not, anyway, the point is that this has been very successful, like 80% of the literature, but it's also 0% of the possibilities. So, so the L tile is not here's an example. The L tile is not an aperiodic monotile because it can form periodic tiles, but it also can form these special non-periodic tilings of a very specific kind, where we have this kind of hierarchical rule for how to take the shapes and then subdivide them and make them. And what we end up doing, it takes a little bit, you can imagine that this is going to define tilings by making larger and larger inflations. That's actually not quite as well defined as it sounds. So, but nonetheless, we can describe these tilings that result in, so one way is that the L tiles, every individual L tile is within a uniquely well-defined hierarchy of L's. So this red one is uniquely in the next size, which happens to be colored orange, uniquely in brown, uniquely in the yellow, this yellow. But if I pick this one, you can just pick it out. You can see that it's in the 4x4 L. And you can see that that is only this. And we'll take a little more effort. It must be this way around. And then we kind of lose track of the structure. So,
So in the previous one, you could not do a periodic one with those 21,000 tiles.
yes, that's right.
Here you could, okay.
Here you could. So, yeah, this is going to show us how. So in this 20,000, he has sort of something sort of similar to this, like a very simple underlying structure, and then he paints on top of that. That's where all those thousands come from, and that's what we'll do here. We're going to paint something on top of this, and so, but before we do that, why is this necessarily non-periodic? Well, if you look at it, it's because you can uniquely recover these dark lines. These dark lines weren't there in the picture, but they were there implicitly, and so when suppose I have some translation of a tiling. Any translation, there's going to be some what we call super tile that's bigger than this. But remember that every individual tile is in a unique hierarchy, supposedly. And so then well, that's it. That's the contradiction. I mean, you can see it visually, it's a contradiction, but the contradiction is that this tile, say, is in a unique hierarchy, but it's in two giant L's. That's the end of it. So, so these are necessarily non-periodic. And here's a cool little movie. Oop, maybe not. Here's a cool little, you can see it. I can't mess with the slider, I don't think. But you can see it every once in a while it was just kind of winding up. But there was always a flaw. So the L is not an aperiodic monotile, but these two, turns out, by magic, that's to say, by a lengthy combinatorial proof that has nothing to tell you, right? Which I'm sure you are similar this. So, so these two tiles do fit together, and they can only form this hierarchical structure. So the miracle parts I'm skipping, but the sensible parts are easy to understand. But somehow or another, they can only form into they behave like L's, and they can only match up to make bigger L's, and they sort of have this kind of hierarchical sensible markings. So these little markings are going to play the role of a bigger L that the smaller ones. And then somehow the same miracle inductively, then you just have this inductive step. Well, if I could do it on that level, they can only form the next level and the markings again activate. And but why that is again just combinatorial magic. And so in this manner, those tiles can only form the L-tile structure, and so these are non-periodic. And that's pretty much been the style. I'm going to skip a couple of slides real quick, but here's some other, this is of course prior to the hat, maybe still is the most famous example, the Penrose ROMs or the Penrose. This is another one, this is by Robert Ammann, who was a non-professional mathematician who was very foundational and important. And this is another sort of route, which is in general, these substitution tilings are very poorly understood. There's no general theory of how to put these guys up, even for simple cases like convex polygons. I think even a single polygon is completely open. And yet we do know how to construct matching moves for them. So for example, here is this is called the Sphinx tile, and you can make a Sphinx out of 4 smaller Sphinxes. And this collection of crazy markings was the product of my paper there, the 98 one. And so, which is, I mean, 98, all of those theorems there are very generally do everything. It's just that here's an example of how they just, all of those, it's just technology for the term. Feed your thing on the term, cranking up, it's crazy. So that's more or less the state of the art. We can do all kinds of stuff. Skip that. But then the question is, can we do it with a single tile? And I think you know the answer. But the point is this was really on our minds for decades. I mean, this is something I wondered about, of course, for a long time. And so I should say something about this too. So this is an Einstein. So it's a bit embarrassing. But Ludwig Donzer, who was a German mathematician who was involved in this field, in the mid-90s, he coined this term, and he did it. So all of the cheapo, sleazy PR that involved like Einstein wearing the hat tie and stuff was on purpose. Ludwig Donzer explicitly came up with this term in the mid-90s for the attention that it might draw to this problem. So as cheap and sleazy and trashy as it is, whatever, it would work. I think that any mathematician could come up with a PR trick that actually worked as that. It's pretty impressive. It's still nonetheless kind of embarrassing, but nonetheless. There's other examples of this too. So there's a whole literature here of things that didn't quite mean what we wanted. So Conway himself came up. Donzer himself was involved in this idea. Here's a single tile that can tile space, but it can never form a tiling with a finite fundamental domain, because these things are twisted by an irrational amount at every layer. And so, but it obviously can admit periodic tilings in the sense that there's a screw axis that provides some irrational screw motion. So this was like circa 1992, 3, where people were like, no, that's not what we meant. And so, but it took a while to understand what it was. So here's another, this is the example I showed earlier. This was also not what we meant. Here, though, there is again no compact fundamental domain possible, because every one of these tiles, so this is in the hyperbolic plane, and these are all congruent, and every one of these tiles has 1 in and 2 outs. So there can't be any compact fundamental domain, because if there were some group that acted in this way, we could take its quotient. We have some surface that's then covered by these tiles, say n of them. We have n ins and 2 n outs, and n would have to equal 2 n. So that's either 0 or infinity, I guess. And so, but this does allow infinite cyclic actions. You can just sort of have the one that has this axis going up forever, and then the geometric dilation here is a translation in the space, hyperbolic space. So that's also not. And there's other tricks that we didn't want. This was amazing. This was an amazing example. This is also a single shape that can only form non-periodic tilings if we are careful with the overlap. The thing is that this tile can overlap itself, and that's it. And the markings have to match itself. So really, some very close calls. And this is already also 25 years, almost 30 years. And then in 2009, we had this one, which is a single shape that can form tilings that are not only non-periodic tilings, but it relies on a rule that this little arrow has to match that So either you can interpret this in lots and lots of ways. There's lots of ways to get around it. One way you cannot get around it with is a single shape that's a physical shape. You can do other tricks. So you can have tiles that aren't connected, or the rules aren't neighbor to neighbor, or you can have layered tiles, but it's still not quite looking at. And then this is an example, you can't quite see it, but by Walton and Whitaker in 2021, so just 3 years ago, where this is a single shape that is also an aperiodic monotile, but the rules are kind of a little complicated involving the way that these arrows work. And so again, you can't code this with a single shape. So that's pretty much was the state of the art. I'm sorry. And so here we are with What's. And I'd like to say a word about Dave. So Dave is one of the questions that's come up a lot for all of us is, okay, Dave, what kind of mathematician is Dave? As professional mathematicians, as research mathematicians, we're frankly protective of our prerogative as research mathematicians. There's been this whole thing, like, I see, and it's weird. It's like, actually, the more it goes on, the more I think of it as just kind of weird and classist and strange. And so, like, because in tiling, there's this whole history of really foundational and important examples that are coming from the outside of academia. And I've actually shown several of them. And at the same time, too, Dave, he's not, I don't think he went to college, but he's very much aware of most of the things that I said in this talk. And he knew where to look, and he knew what he was doing. And so, what kind of mathematician is he? He's a mathematician. That's what kind of mathematician he is. So, like, this is, I mean, it's weird to even have this as a topic, but this is something. And moreover, the more I think about it, like, I think that this kind of discovery required somebody outside of academia to do it, right? Because we would have been fools to do what he was doing, which was just spending years after years just playing with examples just because he liked it. And moreover, but that said, he did know he wasn't just doing this blindly, and he had clear intention. He knew what he was doing. He knew he had some real insights. And so I just want to clear that up. So anyway, but it does take academic mathematicians to interpret this result. So this was kind of a real marriage in some sense of different areas. And so he contacted Craig, and they contacted me, and then my main contribution really in the first phase was to suggest that we contact Joseph, that was true. And so Joseph did a lot. And also the tiling listserv is very important too. So there's one thing that maybe in your area of combinatorial, whatever kind of combinatorics you're doing, might be amenable to it, but it's particularly good in tiling, is that we set up on purpose 20 years ago, deliberately knowing this relationship, that we could have a place where non-professional non-academic mathematicians and academic mathematicians could hang out, talk. And that's really that's how we're connected. And so I don't think we realized that would be as important as this. We kind of dreamt of it that, but it was, I mean, I think that's really, I hope that might be a model perhaps for other kinds of areas of mathematics that might be amenable to that kind of thing. So that said, it's like 47, 49 past.
Yeah, but he would upload the file.
Okay.
Because he was started late.
Oh, that's true. I did start late. Well, now we're actually getting to the hat file. There's a lot to talk about, getting to this. And so I'd like to just spend a few minutes discussing the hat tile itself and the discovery, and a little bit about the proof or proofs. So also, though, I think it's interesting too, because I imagine that at least some of you might well be involved in doing, are any of you involved in like computer searches for this kind of thing, or that sort of interesting thing? Yeah, so some of this will seem familiar in broad outline, but also there's some interesting technical things about the relationship between the human part of the proof and computer part of the proof. So this is sort of so Dave saw that there was something interesting going on. He contacted Craig because Craig had software to check for Heesch numbers. That's really what it was. In this list of four of us, Joseph has this long-standing software for checking for isolated numbers. Craig has this long-standing software for checking for Heesch numbers. I'm just long-standing. and Dave had discovery. So So that was really very important. The software tools that had been previously developed were absolutely essential for the proof and understanding. And so the very first thing was that Craig generated this patch, and that at least gives something to stare at. And now the rest of it, I don't know how Craig saw this in it, but he did. And so then we're off to the races. So these the standard proof of that, then there's a sort of a standard style proof, which I'll just describe. So basically, the raw, I really should say the raw combinatorics of the geometry, just the raw shape itself, somehow it forces this hierarchical structure without any additional markings. To me, that's absolutely miraculous. Like so one of those results I mentioned, we have this technology for, given a substitution tile, given these hierarchical structures, we can cook up markings that will force that hierarchical structure to emerge. And I showed you the Sphinx tile, and you undoubtedly thought that that looked like a complicated mess, which it is, right? And so we have this technology that produces 500 tiles, great. But that a single tile could somehow do this by itself, I mean, it's amazing. And I've seen before. So the Berger style proof is, first of all, we have a substitution rule. Here we actually have to prove, say, we have the extra trouble of showing that this is well defined, because the substitution rule is not at all obviously well defined. Because you have, as you substitute, you have weirdly different shapes. And it's not clear that those would necessarily fit together to make properly. And then we have to show that every tile link lies in a unique hierarchy of such of these tiles. And this is standard Berger outline. And in this case, it looks something like this. So just by checking, we somehow we are really the co-authors. Notice that these 4 pieces could be replicated, and that these markings could encode the way that they fit. But there's something else that goes the other way, right? Right. It's easy enough to say these guys can force that, and that these can force the hat tiles. The magic, and what requires quite a lot of computer analysis actually, is to say the other way around. So given the hat tile, just by examining local configurations, that every hat tile is uniquely in one of these configurations that uniquely can be rewritten these markings.
So the same way with the L, you could figure out where on the L you were.
Yes, that's right. So with the L, right, so there's 2 steps, right? There's one step to show that these guys behave the way they should and they form the right structure. And then the flip side is that the only thing that, actually what's really different is the L can do all kinds of weird stuff with them. Here the hat tile, the only thing the hat tile is actually formed into these clusters. And these clusters can then only form with these specific behave this way. And so that's a totally unseen before thing. And that required a lot of computer analysis just to enumerate, not too bad, just enumerate patches of radius 2 and just check it. So just to speed up, I just want to point out, like, here's a whole bunch of, we have these substitution rules. I guess the point is that we had to show that these are well defined. That was a pain. And then this is, I guess, again, I want to emphasize not the details, but rather that there are a lot of tedious, pointless details. Because it's sort of a hallmark, right? I mean, it's people, I'm sure you all encounter these kinds of things. And so we eventually got through that. And so in particular, we had shown that the metatiles can only form hierarchical tilings. And then I guess I already said this. And then to show the hat tiles aperiodic, you have to then show that the hat tile can uniquely co-host in the metatiles. And so that just turned into its own mess. So one of the remarkable things that came out of this, though, was this incredible continuum of tiles. And that was, again, also something none of us have seen before. And with a second candidate, Einstein, in fact, the whole continuum of these Einsteins. And it turns out that they're essentially all combinatorial equivalent. And this notion of combinatorial equivalence is a new one to us because it hasn't come up before. And I'm not going to really go into the proof, but it turns out that the way to understand this is that there's this really interesting incommensurability between triangular grids that are scaled by root 2. And the way that this basically works is that that movie I just showed you, on one end of the continuum is a tile that's this shape, and the other end of the movie is a tile that's this shape. And if there was a period that preserved both of them, if there was a single period that preserved both of these up to at least some affluent, then we would have to have two triangular grids that are scaled. This one has 4 triangles, this one has 8. So the lengths are just, this is just scaling by root 2 in the lengths. So we'd have 2 triangular grids that are scaled by root 2 to one another. And you can believe that it doesn't, and it's just a matter of checking that it does. You'd have some mess like that. So without going into the details, I'm really not meaning to explain that super well. But just to emphasize that there was a second additional proof. And then just to conclude, or come to the conclusion, I think you might know that there was this whole question of whether or not it counts whether a single tile can be flipped over or not. And honestly, it didn't, I know this sounds naive, but it did not even occur to us to care until after we were reminded quite vigorously by the internet. And the reason we didn't care, well, first of all, like, you see 2 shapes here or 1? I mean, there's 1 shape, obviously. You have to work to see 2. And but then I think, this is as good as it gets. I mean, in mathematics, we have Euclid. So side angle side says nothing about orientation. And you can see why, because God, can you imagine if we had to worry about left-handed or right-handed triangles? It would be horrible. And there's a little joke. That's even more authoritative. But of course, in physics, it does matter. So what we really did for physics, biochemistry, and of course, in reality, there's no, in all physical things really are handedness, do have handedness. So it's fair enough. But we were very fortunate that the specter just kind of appeared. And this is in that continuum. This is the one moment where all the edge lengths are equal, and so it allows possibility of being flipped over. I'm sorry, if we allow the possibility of flipping it over, it actually does tile periodically. And so this is why Dave is a mathematician. I mean, I'm a professional mathematician, and there were 3 PhDs on the team. It was Dave who had the insight, which is obvious in hindsight, which is that because this has more flexibility than just by restricting the isometry group, maybe there's still enough combinatorial juice that it could be interesting to look at where this has only rotations. He said, and he was right. So of course he's a mathematician. And so that quickly became its thing. And I won't explain any of this. I just want to say that in the end, this turned out, in absolute hindsight, this turned out to be the right picture, which isn't actually in the paper, which is at least in the half paper. But in each case, what's really going on is that these are combinatorial hexagons. And then there's 2 flavors of combinatorial hexagon. This is true for both the hat and the stick. And one of the flavors is made up of 2 tiles, and all the others are just a single tile. And what changes here is just simply the way that they fit together. And there's some number of them, 9, and there's substitution rules on them. And this is the best way perhaps to look at what's going on. And so anyway, just to kind of wrap up. So this remains open. It remains open whether or not the monotiling problem is decidable. We don't know anything about the asymptotics. It's like a one-off. I mean, it's hard to imagine that it could be a one-off, but there's another thing too, which is that these tiles were not humanly thought of. They weren't designed. I think of them as found in the wild. In fact, that's true of these as well. And so because they were found in the wild, that is to say, there wasn't a human intention behind them. I think that they exhibit behavior that we couldn't have imagined. And so how much, that's sort of exciting and interesting. Do we have more surprises of this kind, or what really is the general picture? I mean, we obviously have no idea. And so I think that's a perfectly fine place to stop. Here's Joseph's data from 20 years ago. You can see that it's just this is 12 digits, 13 digits, I think. And for tiles that he's checked. And again, this is, I'm showing you 3 interesting examples. So it's a good place to stop.
Thank you, that was great. Questions?
How did you find Dave Smith?
Yeah, we did it. We just started the Euclidean listserv. We formed a community.
It just showed up.
Just showed up. Yeah, eventually. I mean, it's been around for 20 years, so it's actually very vibrant. If you're interested, case CEman use. Yeah, so so it worked. I mean, I don't know. That was a big surprise that it actually worked. It was like sort of an early warning system.
How did you describe that? Is it like exact angles, or how does that 2013 sided shape?
Yeah, so actually I've been practicing drawing it. So, because one thing I really want to do, I don't think I can do this trick. This is like a party trick. But one thing that, all over New York City, we have these hexagonal pavers. And I would just love to do this as cycle party. So let's, with kids. So here's, I was trying to remember how this. And then there's one more. It is here. That's it. Oh, I can do it. So I guess this algorithm works. That's great. So that's cool. I don't know if you're impressed with that. I just started practicing. So this is the hat.
Yeah, yeah. That's very nice.
So the way I actually did that, the way I remembered that was it's like 2 back-to-back thirds of hexagon. And then I continued and put in another third here. And then I just remembered that from this one. So I guess that works. I guess that's a follow procedure. But yeah, but one thing that's really astonishing, I guess I don't have the slide in this example in this set, but let me just grab another one. See if I can find it here. Yeah, so here we have, this is kind of really bizarre. This is like in that movie, right? This isn't quite the same picture. This is just with the specters alone, but it's so strange that when you can change these edge lengths, right? And you might ask, well, can I do that? And will I remain having globally well-defined tile, right? I mean, if I changed the local combinatorics, like in what sense do I know that I'm gonna have a well-defined global thing? Like, right, you watch the movie, why should it be that I can change these edge lengths and just screw things up so that things don't fit together anymore? And it's like one of these miraculously and unsatisfying answers is because locally you have if you just think of it as a complex, you have a well-defined abstract complex that's just got some combinatorial data. This graph, it's just a complex, cell complex, which happens to be simply connected, unbounded, complete. And that's it. And then moreover, then changing the shape of the edges, then you have a local geometry that you can chart. It gives you an atlas. So you can put that out, you can chart the geometry onto that complex. So now you have a constant, zero curvature, complete, unbounded, simply connected complex. That's called the Euclidean plane. Isn't that cool? So it's like some miracle out of so it's kind of funny that I don't know, I just found that so strange because we really struggled with that a lot. Like the well-definedness of these things wasn't really obvious to us at all.
So what's next? What do you plan to do next?
Me personally, well, so me personally, I was not looking for an aperiodic monotile because I'm not got foolish. Because I was maintaining an academic career. I mean, I think that gets back to that. But also, I'm no longer doing that anyway. So for me personally, I feel like I need to work on, I need to sort of do some general housekeeping for the field. But mainly I'm having fun. Back to, if you want public facing things, of course, the museum makes me.
Do you hold proof by hand, or does it actually require computers?
That's a great question. So, the scale of the proof is really interesting. So, let me just say a quick word first about proof complexity, because we have these decidability things underneath it, right? You expect that if you were to enumerate examples, that you would have the complexity of the proof would occasionally copy, like you have any computer bound that occasionally blank the proof would have to copy about it, which is one of these crazy paradoxical theory of computation things. So the example I showed with the L tiles is the two tiles that force the L tiles. Those actually have a remarkably lengthy but still human scale proof. It might be a simpler proof, but the proof I know is already really tedious. So with the hat, it seems like the situation is something like this. Well, Joseph found a proof that doesn't require any computer stuff. So we actually do have a proof that doesn't require any computer stuff, but the traditional proof required extensive case checking, which is, I would think, is probably within humans. Like it's actually something you can do within a week of utter tedium. It's not like the 4-color theorem first, where just hope. I mean, so basically it comes down to checking maybe just a couple hundred cases. So I would call that human scale for jail. I mean, I think those are useful questions to consider. And I think a lot about the complexity of these, and because in the asymptotically, what you might expect to see, right? Or occasionally, and I'm sure you see this in many of you in your own area, is the occasionally you see these utterly simple and tractable examples that just should pop up, and you might be expecting this. And so the hat has already this kind of really complex combinatorial proof is terribly surprising.
Are there any more questions? Maybe let's ask Peter if there's. Peter, do you have any questions?
I don't, but I certainly enjoyed the talk, and I appreciate the opportunity to zoom in.
You're welcome. Yeah. So that's it then. Should we wrap up? All right, let's thank you. Bye, Peter. We'll end the meeting then. Bye. Yeah.
So